true love, Princess Peach. Peach is so cool, and with my star we're gonna rule. Peach, understand, I'm gonna love you till the very end. Peaches, 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 peaches. Oh, yeah. Oh. Mario, Luigi, and a Donkey Kong too. 1,000 troops of Koopas couldn't keep me from you. Princess Peach, at the end of the line, I'll make you mine. Oh, peaches, 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 peaches. Oh, yeah.
All right. So, I don't know if there were ever sometime in your life you were fascinated by the game called Super Mario. Uh, so, to be honest, there is a link. Well, there is a link between how I become a good student and Super Mario. So there was once when I was like first grade in elementary school, and at that time, every day after class, all I want to do is like I just ride my bike in the neighborhood area. Until one day, I visited my cousin's place, and then I saw him play the game console, and the game was right Super Mario. And I was like, oh, I want it, I want it. And my auntie said that, okay, so if you can ace the final in your class, then I will give you one as the present. And I think, okay, then I want to know, like, I want to ace the final. So I tried really hard. And I remember clearly I was the third place in the class. And I didn't receive one because like at the end, I was like trying to tell my auntie, hey, I got third place. Oh, okay, you're doing great. And then she didn't say she's going to give me a console. And then I came back. I was thinking, okay, is that because I'm not the first place? Right? So then I tried really hard, and then I gradually become the second place in my class, and then first place in my class, and until I finished my high school, I never received a game console from my auntie, and my first game console was actually coming from my first part-time job, well, full-time job in summer as a summer intern engineer. In some company. So, but you know, that's my link to Super Mario. I don't know if you have a link to Super Mario in your life, and you might wondering why am I pulling up Super Mario in the very beginning, because there's actually a link between Super Mario and our lecture today. So before we start, we are going to starting from this lecture, we are going to see a new component in the computer system. As we mentioned, in volume architecture, we have we have three main different types of components. And in the last lecture, we have been talking about how important and why I keep including storage in the big picture, because right now you cannot imagine a system without virtual memory. And the virtual memory is pretty much resides in the secondary storage. So that's why you always have to include virtual memory storage in your big picture. And the main memory, as we said, is simply serve as the cache of the data from your virtual memory. And in all previous lectures, we focus on those memory problems. So remember, we have caches so that we can keep most important data in places nearby the processor. And we have TLB because we want to accelerate the process of address translation. So we have finished almost everything we want to talk about regarding the memory. So if we solve the problem on the memory, which is the most critical part of the MDOS law, then the remaining thing that really matters are going to be the processor, which has to fetch instruction from the memory and then execute these instructions according to their program order, and based on what the instruction wants us to do, we may access data. And gradually, we would advance the program counter to the next instruction until we finish the program. And what indeed a processor is. So from the high level perspective, since we have many different types of instruction, you can consider the processor as a collection of functional units that can perform each instruction accordingly. And by saying that perform each instruction, it has a certain circuit in the hardware to accomplish the task that each instruction wants us to do. And the abstraction that allow the software to employ those functional units is indeed those instructions. And the set of instructions that are available to the programmer are called instruction set architecture. So most of the time, programmers don't directly write at the level of machine instruction. So most of the language runtime or compiler will do that work for us. And with that, we can use more human readable approach to compose your program. So that's the high level perspective of how we use the processor. And before we start, I just want to ask you, how many of you ever had the coding interview experience, and what kind of question have you been asked? Do anyone want to share with this respect? What kind of coding question has you ever been asked? Or none of you have intern experience? Who has intern experience before? Okay, algorithm questions. What kind of algorithm question?
I forget. I remember there was one about matrices.
Okay, matrices. Okay, who else?
Hash.
Hash. Okay. Okay. So sounds like, what are you okay to reveal what company is that? What kind of company is that?
I forgot. It was I think it was JP Morgan.
Okay, JP Morgan. Okay, sounds like a more normal company. So the thing is, why am I pulling this up? Because many companies, as I mentioned in the first lecture, a lot of companies, especially those companies, they want to test people's ability in C or C++. They would sometimes give people puzzles like this, like give a fastest way to multiply any numbers by 9, how to measure the size of variable, how to measure the size of any variable like this, and write cos9 bit to swap two variables in 5 different ways, etc., etc. And a lot of engineers, they are so proud that I know how to solve these problems. And because they thought this is a more efficient way of doing things. But is that true? Right? So let's pick one of them. So for example, and in fact, I found on the same web page, they say, hey, this is the most, right? It say, this is the most efficient way. Did you see that? The most efficient way, right? It says the most efficient way, right? And a lot of people, I know when you prepare your midterm or when you prepare your exam, you like to ask website, you would like to ask Google, there's nothing wrong with it. But one thing that I think is really important is that there's no one verify those information, right? And apparently, for this one, we can show it on a demo, right? So for example, why is the font is okay? Here we go. So for this one, I don't think that's the demo I want. Let me see. Do I have it somewhere? What was that? No, not this one. Okay. Okay, for this one, right? If you remember from your vague memory long time ago. Hello? Oops. Right, if you try to pull up your memory a long time ago, right? We did mention, so all right, give me a second. I really don't like the feeling that I spent quite a few minutes wrote this demo and I don't get a chance to show it. Not this one. How about this? No. No. Wait a second. What was that? Pipeline. Ah, shit. Here we go. Okay, so let's see. Okay, so this is the okay, so this is the mess of programming that a lot of people would have, right? So like the right hand side is indeed the one that blog post suggested, and the left hand side is the one that you would write most of the time, right? And what I'm doing here is that I'm trying to flip the array, which would use a lot of swap operations. And now I'm running each for 10 times, and let's see what the performance looked like. And if you pay attention to the performance, right, the version A is the one that people will consider to be less efficient. And version B is the one that people will be considered more efficient. But if you check the execution time, most of the time, on average, there's no difference. And in fact, if you pay more attention, you will find most of the time and in more instances, version B is actually slower, which means that using exclusive OR doesn't give you any benefit in performance, and in fact, most of the time it's harmful, right? And also, if you can remind something that we learned in the very first week, this one is ironically faster than not the version not sorting it. And after the memory lecture, there is still nothing we can learn from here to explain that. Because if you think about the locality of traversing the data, there's nothing different from the sorted version and not sorted version. And in fact, the sorting would actually increase the instruction count. So why is this faster? So starting from this lecture, we are going to gradually give you an answer on this. So in this, for this series of lecture, for the lecture today, we are going to give you a recap on the concept of a processor, and we are going to talk about the most modern design, the approach most modern processor would take, called pipeline processor. However, there's nothing perfect, so we are going to talk about what makes pipeline processor imperfect. Before we start, right, talking about the pipeline processor, I want you to remind yourself, if I want to design a processor to execute an instruction, and assume I already have those functional units available, what kind of hardware operations do I need to do within this processor to execute the whole instruction? So if I want to execute the instruction from the processor's perspective, what's the very first thing that I need to do? What do you think we need to do very first, in the very beginning? Without this, nothing can start. What's the beginning of the life cycle of an instruction in a processor? What? Load from memory. Okay, perfect, right? The first thing is actually we have to get it. Otherwise, we cannot start it, right? And there is nothing in the processor originally. So we have to fetch it from the memory. Okay, what's after that? Any idea? Decode the instruction. What does decode mean? It's already binary, right? The assembly is a human readable interpretation of the binary. So in fact, when they are in the memory, they are already in binary format. So tell me, what's the next thing to do after we fetch the instruction into the processor? So decode, but what does decode really mean? What's decode? What's decode? What did you learn from the reading? Okay, so decode, right? It's a collection of the following things. First of all, you have to know what is the desired operation and what are the operands that we need to execute this operation. So that's one part of the task in the decode stage. So decode means that right now the processor has to look into each instruction, parse the instruction, figure out what kind of operation this instruction wants us to do, right? So that I would know what to do for the following, as well as knowing where my operands are coming from. So for example, if one of my operands is a memory operation, then I have a memory address, then I know that for this instruction, I probably need to send it to the memory pipeline first, right? So the second thing, right? Because once we decoded this instruction, the next thing that would come up is that we need to drive the corresponding functional units for that instruction. So, but before we can do that, we have to figure out, are we ready yet? Do we have the value there yet, right? And so the next thing to do is that we have to pull up those register values that the instruction needs so that we can put those values as the input of our corresponding functional units. So these two things together is decode. These two things together is decode, right? So like in a final, I'm not going to just ask you what the process is to do, and you just tell me it's decode. Sorry, I'm not going to give you any credits because you didn't tell me anything about what decode is. You have to tell me. You have in a decode stage, we have to parse the instruction, knowing what operation we want to do, and prepare the operands and access the register file, right? So these are the two things that we need to do, right? Now we got everything ready. So what's the next? What's the next? Execute, right? So we can execute this instruction in functional units. And by functional units, depending on your desired operation. So that's why you have to know the desired operation first, right? So some of the desired operation, we may want to use an arithmetic ALU. And for some of the instruction, for example, if I have a conditional branch, and that's the time I use the input that I have to judge if I want to change my covariant counter or not. And the other thing is that for the conditional branch is also the time that I'm going to generate the target address for the upcoming instruction. So that's for the branch instruction. And also for memory instruction, at this stage, you still need an ALU to help you generate the effective address that you need to access the memory. So remember, in x86 or in any kind of instruction set architecture, we always provide this kind of addressing mode that you can give the processor a base address and an offset, or in x86 it is even more crazier that you can also put an index in your memory addressing. However, you need an ALU to calculate the effective address because you have registers as variable. You have index as a variable, and both would not be able to know the exact value at a compile time. So it has to be determined using an ALU. And with that effective address, if it's a data memory access instruction, then we can access the data memory after the effective address is already generated. And finally,
no matter it's a read instruction or an ALU instruction, we need to propagate the result to a later instruction to continue computation. So the place that we would put those results would be registers most of the time. So at the very end of a memory read instruction or an ALU instruction, you have to write back the value to the destination register so that the later instruction can use it. And finally, once you're done with those, another thing don't forget is that we have to update the PC, right? So if you don't update the PC, you are just going to, your processor is just going to keep fetching the same thing. So by updating the PC, there are two different ways. So for example, if you have a branch instruction, and if the branch instruction decides that we want to take, the branch outcome is taken, it means that we are going to change the execution flow of your program. So it's either jump to a further place or jump back to a place that is priority to the current instruction in the compile order. But otherwise, if it's branch not taken or is anything else that's not branch, then you should go to the next instruction. And for like ARM or RISC-V, you are probably going to be PC+4. But for x86, which we use in this class, it doesn't always to be PC+4. Sometimes +1, sometimes +7. It could be it varies a lot. But the idea is that you have to update the PC before you can move forward. So as you can imagine, right, on the hardware perspective, if I want to support all of those, the very first thing is that since we want to fetch data, so the very first thing is that a fetch instruction. So you have to start with your instruction cache. But where in the instruction cache that should I fetch? You need a register called program counter. And a program counter is the input to your instruction fetch unit. So that program counter will tell you where in the memory should I get the instruction. And the instruction fetch unit get instruction from the memory, and then you can decode the instruction. And with decode, you will figure out what's the desired operation and what are the register values that I need so that you can send those to the register file, and the register file will give you the corresponding outputs. And those would be the inputs of the functional units that your instruction need. And the functional units will perform the desired operation and give you the outputs. However, for the outputs, some of them we need to write it back to the register. And for branch instruction, your output is essentially the next PC. So you don't write to the register, however, you need to update the PC. So those are the basic components of a microprocessor. And one big difference between CSE141 and 142 is that this is the level that you need to know. But for 141, you probably have to know more than this. Okay, so with this, in a very basic clocking mechanism, the most naive implementation of the hardware is that let's execute one instruction per cycle. So if you pay attention to the animation, right? Like once we receive a clock cycle signal, the instruction would go through all the functional units that it needs to use to perform the desired operation. And this instruction, everything that this instruction needs to do has to be done within a cycle. And once we are done with the cycle, then the next instruction can start executing. So that's the basic clocking mechanism, basically a basic single cycle processor idea. So as you can imagine, for this kind of processor, every cycle we are completing this instruction decode, a fetch, decode, execution, write back, all these things together within the same cycle. So and instructions are executed back to back. So you can imagine the CPI is always 1 in single cycle processor because every one cycle I execute one instruction. However, your cycle time is pretty much the maximum of
the execution time of each instruction. So that's the design of the most naive processor. However, nobody is using that because it's very inefficient, right? So, and the reason is because you can imagine how, like, if you are going to buy a coffee at the coffee shop, for example, like the one nearby the bear, right? There's always one person there, right? So if he or she is busy working on the customer, you have to wait for the microwaving stuff to be done or whatever the previous customer needs before the attendee can serve you, right? So that's very inefficient, right? So another approach that is more popular nowadays is called pipelining. So what is pipelining? So pipelining is not about this, right? Because if you think of Super Mario, right? He's like a pipeline worker like this. However, the pipelining that we talk about in computer architecture or in general in hardware design is that we divide a complete data path into different segments, by which we mean that each segment, they can work on different things at the same time. They can work on different things at the same time. And for each segment, in between each segment, we use a pipeline register to buffer the temporary result of the current task. And at each cycle, instead of finishing the whole thing for the complete instruction, we only perform part of the job for each instruction. So that's the basic idea of pipelining. So here is the view of pipeline. So saying that we have a few things that we want to do, like 5 things that we want to do for an instruction. So with pipelining, you basically have the clock connecting to each stage, or say each segment of your circuit that perform the partial task of an instruction. So whenever a clock signal comes, the pipeline stage only make progress for an instruction partially. So for example, in the very beginning, we have nothing, and now after the first clock cycle, the first part of the circuit start to work on the first task, for example, the red. And then in the next cycle, we advance the red to the next stage of its desired operation. And in the meantime, the original hardware circuit that worked for the red instruction can be freed up to work on the orange instruction. And gradually, you can see that the pipeline would be filled with 5 different instructions for this example, and each of them would be working on a different instruction and at different stage. And the beauty thing of this is that in a previous design, your cycle time is pretty much the whole thing of an execution. But right now, because each cycle, I only need to make progress for each divided stage. So the cycle time can be shortened to the longest stage within this pipeline. So you can imagine the throughput would be a lot better. So if you still have a vague idea about what pipelining is, right? Think about Subway, which is probably the place that you will go to with the most efficiency when you are short on time during lunchtime. So for Subway, it's pretty much a pipeline, right? So in the very beginning, right, the very first stage in the Subway is that there will be will be someone asking you, hey, what kind of bread, right? And then once you answer the bread, the attendee will ask you, do you want to toast it, right? And then the oven is pretty much like a pipeline register at some point, right? And then your stuff will be put into the oven, and then the same attendee will work on the next customer, keep asking what's the bread. And you are pushed to the next person, and the next person would grab your bread from the oven and ask you what kind of protein, right? And then you probably ask like chicken breast, right? And then do you want cheese, right? Do you want Swiss American, right? And then you will be put into the next person, and the same person will serve the next customer.
and you will be put into the next person. Hey, what kind of vegetables, right? So do you want like pickle or whatever? I hate pickle, so. And then once we're done with that, you will be put into the register and pay, right? And also, if you want a soda, that's also the good time to do it, right? I just want to, so that's, if that gives you a better idea about what a pipeline is, right? Like Panda Express, Subway, they all use this pipeline system. For what? Because it's more efficient, right? So, okay, with pipeline execution, you can pretty much imagine this is what our processor would look like. So as I said, to divide the task data path into different segments, we have to put a few pipeline registers. So right now, we add pipeline register in here. So the most common partition is that we just partition add instruction fetch, instruction decode, and register. And then the functional units, and for memory, we separate a memory stage from the address generation, because address generation, as you can imagine, it needs to perform this arithmetic, so it would take as much time as other arithmetic as well. And finally, write back the result. So based on this, you can pretty much imagine these 4 places are the places where we are going to put pipeline registers. And with those pipeline registers, you can pretty much imagine whenever I receive an instruction. So in the past, when I see this clock signal, you will see my instruction going all the way through the end of the processor back to the register. However, right now, it's only staying at the instruction fetch stage. In the next cycle, the first instruction would advance to the instruction decode and register preparation. And the second instruction, which is the blue one, now being fetched. And now the next clock cycle coming in, the purple instruction go into the execution. And we fetch a new one called green. However, the original blue instruction is right now moving to the decode and register preparation. And now the new clock cycle coming in, we got a new instruction called orange, and that would force us to push the progress of green to instruction decode and register preparation. And in the meantime, the purple instruction finished execution, so it's right now putting its result to the register. And the blue instruction can use the functional units that the purple one freed up. And when the next cycle coming in, every instruction advances 1 stage, and the purple instruction is finished, so it's vanished. So you can gradually see that's how the instruction would evolve, make progress in the processor. And every 1 cycle, we only make partial progress. However, compare against the previous one. Within a single cycle, then a lot of the functional units are not even functioning during this long cycle time. But right now, it seems like every part of your processor is busy working on something at any given time. So you can imagine the throughput is a lot better. And another way to look into this is that we can draw the progress of your instruction in a timeline. So if you look at this, right, and assuming that every vertical square space is basically a cycle, you can find out that after a certain cycle, every cycle we are going to produce the outcome of an instruction. So the CPI is still equal to 1, because every cycle I'm effectively generating the outcome for an instruction. However, the beauty is because the cycle time is right now only this instead of this. So we can actually speed up the execution in proportion to the amount of cycle time that you reduce. So that's the ideal of pipeline. However, there's nothing perfect. So can you identify the imperfection in pipeline execution?
right, let's take a look. Okay, so obviously we need some discussion. So why don't you go ahead to discuss with your friends to see why can we generate result back to back? All right, let's take a look. Okay, after discussion, seems like most of you are satisfied with B. So it means 2. So what are the two pairs of instruction that you guys are thinking could be problematic? What are the two pairs? Three and four. Okay, in what way? So the thing is, right? So although they are both added instruction, so they, because of pipeline, right? So you can imagine once, because this instruction is coming earlier, and this instruction is coming a cycle late, right? So after this instruction finished, after instruction 3 finishes execution, it will free up the functional units for instruction 4, right? Now, the second question is that, do you think there is anything that instruction 4 needs an input from instruction 3? So instruction 3 use ECX and EAX and put the result in EAX. And instruction 4 is doing RDI plus 4 and put the result into RDI. So do they have any relation? No, right? So they are completely independent, right? So probably not 3 and 4. Other thoughts? 2 and 3. Okay, so for 2 and 3, in what way?
So line 2, like, puts the competition into ECX, and line 3 uses ECX to add.
Okay, so line 2 is a memory instruction that reads data from RDI, the memory address that RDI pointing to, and put the result in ECX. And that's the input that the next instruction needs, right? And if the second instruction doesn't wait, I might get a wrong value, right? So this is definitely one pair. Okay, what's the other?
4 and 5.
4 and 5, right? So for 4 and 5, again, right? So 5 needs to compare RDI, right? And 4 generates RDI. However, based on our pipeline, the RDI is not visible until this instruction put a result in the target register,
right? So if I go ahead and execute a compare directly, then I will get the wrong comparison. So those are the two that you guys agree, or do you have other thoughts? Do you guys have other thoughts? Why isn't 1 is not combining with 2 and 3? Oops. So what's the problem? Why do you think there will be an issue?
Well, because on 3 you add ECX to what's in EAX.
Mm-hmm.
I don't know. I thought pipeline is whatever instruction you use prior. So then, yeah.
But here's the thing. Am I going to receive the EAX value before the XORL here generates the EAX value and put in a pipeline?
So you mean it's done, like number 1 is done already, so EAX is already set by the time number 2 is done?
So it's done, but have we written back the value in there? So your original intuition is actually right. Not yet. So how do you know this? So in a lot of cases, I can only say, don't be lazy, right? Like prior to the midterm, a lot of you ask me, can I not writing a sequence of address? And if you review your midterm, whoever didn't write the address sequence would get terribly the wrong result. Definitely there are, like if you are an expert like me, right, I can look at real quick and I feel like, okay, I can use my intuition to tell you this is probably roughly the range. But to be safe, right, always that's draw the pipeline diagram as I just suggested, right? So let's go through that. So for the pipeline diagram, you should assume the horizontal axis is the time. And the vertical, well, or one of the axes, because later on, when we execute more instruction, I'm going to flip the pipeline. So saying that for this slide particular, we have the horizontal axis as the timeline, and the vertical axis as the instruction that we want to execute. And in each intersection, it will tell us the progress of the instruction right now. So at the very beginning, the pipeline is empty. And we have the very first instruction that we need to fetch, right? So put a fetch here. Now, we are done with this cycle. In the next cycle, right, we can advance the first instruction to instruction decode, which means that we can, we figure out this instruction is an XORL, and we want to prepare the value of EAX to the LU. And at the same time, because we free up the fetch unit, so we can fetch the next instruction. And it's safe to do this because the previous instruction is not going to change your program counter direction anyway. So it's always safe to fetch the next instruction at this point. Now, at the next cycle, right, we are going to execute the first instruction, which means that we are going to occupy the LU. And for the second instruction, we are going to check what this instruction is and if we are ready. And now we free up the instruction fetch unit, and everything should be fine. Okay, so now at the fourth cycle, because the first instruction is not waiting for anyone, so we can definitely write it back. And for the second instruction, do we depend on anything from the first instruction? Are we occupying the same hardware as the first instruction for its write back? No. Okay. And so we can safely advance each instruction, right? So far so good, right? So as you can see, the first instruction completes. The second instruction is at address generation stage. For the third instruction, right now it's in the instruction decode stage. And what is our task in the instruction decode stage? what do we need to do in instruction decode? So that's why I have that question in the very beginning. Operand, right? We want to check if the operand is ready, right? So at this time, our operands for instruction 3 is ECX and EAX. So S86 is kind of abnormal in a way that they only have 2 registers, and both registers are also the source. So EAX and ECX, they are both the source. So ECX, is it ready? If we go ahead and execute this instruction, are we going to get the ECX we want? And if we want to go ahead and execute this instruction and pull out the current register file, are we going to get the EAX we want? Yes? We are writing back at the top, but I'm also decoding right now. So am I getting the right value? So it's uncertain, right? Because right now I have an issue here. Both 1 and 3, one want to write to EAX, the other want to write want to read EAX, right? So there's a conflict here, right? One want to write, the other want to read. So for those of you who've taken CSE140, you will know this is not a behavior that the hardware would accept. Otherwise, you are going to generate some random signal that will mess up your register. So this is not going to happen. And even though we let go this, looking at instruction 2 and instruction 3, as what Owen just said, because we are also waiting for ECX, right? So we cannot make any progress, right? And for the next cycle, right, if we continue execution, there's another problem. For instruction 2, it wants to access the data memory. And for instruction 5, we want to fetch it. However, if you remember the current processor design, we only have 1 unit of cache. So we are going to have this conflict again, right? And who is going to grab it? So some of it needs to wait, right? So we cannot output the result back to back. Otherwise, there will be something bad happen, right? And the other thing is that the ECX is also not ready for the add instruction to execute, right? So it's not going to work out. Now, if we continue, what's going to happen? Let's look at 2 and 3. So 2 is a memory access instruction. It needs to do 5 things. And 3 is an LU instruction. It only needs to do 4 things. And because of this unequalness, unfortunately, now they all hit to the write back. However, we only have 1 set of hardware to perform the write back operation. Another conflict, right? So if we keep going, right, you can see more issues here, right? So for example, again, there's data not ready, right? And again, even though at the end, right here, I have a jump instruction, branch instruction that I don't know where's the destination. And before I know the branch outcome, I should not fetch any instruction, right? So if you count this 1, 2, 3, 4, 5, 6, right? There are more than 5 things would render this pipeline not usable, right? So in fact, it's for pipeline processor, although it helps to improve the throughput. However, to reach its theoretical throughput is mission impossible because we are going to see a lot of issues there. So these issues are called pipeline hazard. And you know, a lot of cases, people like taxonomies, like people categorize that cache misses into 3 categories. And the good thing about taxonomies is because we can categorize the cause of issues and then we can narrow down the solution that we can take to solve each issue. So in fact, when we talk about what affects the throughput of pipeline processors, there are also 3 types of hazards that we need to deal with. So the first type of hazard is called structural hazard. It means that the cases where we have 2 instructions that needs to compete for the same piece of hardware. That's called structural hazard, right? The most common structural hazard in your residential college life or in your apartment life is probably the laundry, right? A lot of people they don't take their stuff out from the washer, and you have to keep waiting, right? That's a conflict mess because both of you want to compete the same thing, right? So that's conflict, but that's structural hazard. And the second type of hazard is called control hazard. So the control hazard is sometimes I cannot make any progress because I don't know what to do. So for example, right, like for this class, I try to give you guys assignments as early as possible because I don't want you to have control hazards, right? A lot of cases is more about like, okay, I'm waiting for the instructions. I'm waiting for the assignment to come in. I have time. I want to do this right now, but I can't because they are not ready yet. I don't know what to do next. I don't know what to do next. That's control hazard. The third type of hazard is called data hazard, right? So the data hazard is about there are things that I need. For example, I'm depending on, so that's why we don't have group project here, right? So typically, I don't know how many of you have that experience. Like if you are taking a course, if you are doing a group project, most of the time you feel like having a group is actually making the project time longer because a lot of cases you are waiting for someone to give you the portion of the code that someone is responsible for, and then you can do the next thing. That's a data hazard. Whenever you need something that is not ready in the pipeline for you to use yet, there is a data hazard. So these are 3 types of hazards that would prevent us from making back-to-back progress. So right now, let's go back and look at what happened previously. Can you tell me how many of them are belonging to data hazards? All right, let's take a look. Okay, so looks like, wow, the first time we probably don't need a group discussion. So tell me, what are the 2? What are the 2? What? 2 and 3. 2 and 3 on which part?
It's reading the RTI into ESATs, which is needed in industry.
So what is 3 depending on 2?
Option?
What operand?
ECX.
Okay, 3 is depending on 2 for ECX, right? What else?
For 5, the RTI is
Okay, so this too has data dependency. And because of the dependency and because the data can only be available after the write back stage. So we have to wait, otherwise we will get the wrong value, right? So these two are data hazards, all right? But others, right, if you check about this, right, like for 1 and 3 that we are both attempting to access the EAX, for the case where instruction fetch in the memory, they both want to access memory, those are structural hazards. And for the case where we cannot do anything before instruction 6 finish execution stage is because control hazard, right? So this would give you an idea of what a difference among these 3 types of hazard. So just test you one more thing. For this pieces of code, we see the version A is slightly faster than version B. So why? All right, let's take a look. Okay, so definitely we need some discussion. So why don't you guys go ahead and discuss with others and let's see what do you guys think. Oh. Okay, so take a look. Okay, it's a tie. So the answer is B. But why? So here's the thing, right? If you look at what happens on the right-hand side, saying that we have 3 statements, right? So for the first statement is actually performing exclusive OR, and then I put a result into A, right? Which would immediately become the input of the next statement. And same thing for the next statement, it requires to the output from this statement, right? So if you imagine that in a pipeline, everyone has to wait the previous one to write back its result or made it the result available before we can make progress. Agree? So now let's look at the first one. So for the first one, I put the output into temp. And the second statement put its output into A. And the second statement only reads input from B, not from temp, right? So the only dependency here is actually temp for the first and the third. And remember our pipelining strategy. If the second doesn't have to wait the third, if the second doesn't have to wait for the first, it can make progress, right? So actually, the first one would, the version A would typically be faster because they are less likely to incur data hazards. So here are some takeaways so far. So first of all, we have three types of hazards: structural hazard, control hazard, and data hazards. And now, knowing this hazard is important in a way that we want to identify how are we going to address that. And the way how we address that are actually deeply impacting our modern processor design. So let's see, what are the steps that we would take? So the universal approach is definitely, as I just mentioned, when I detect there is a potential of pipeline hazard, I just let the later instruction wait for the situation to resolve, right? So here are the thing, right? So if we just wait for the hazard, you can imagine for the second instruction, since I am, okay, so for the second instruction, I don't have to wait. However, for the third instruction, since I have to wait for the second instruction's output and also the first instruction's output, right? I can just stall for one more cycle. By stall, in hardware, you can imagine we just don't propagate our current progress, and you just don't update your pipeline register, so, and as well as your program counter. So everyone stay at the same place except for the one who is right now the most, the one that can allow to make progress, right? So that's the basic idea of stall. And so if we stall the third instruction for one more cycle, then in the next cycle, right, are we allowed to execute? And the answer is no, because we still have to wait the second instruction to write back the memory result to the register. And then in the next cycle, right, when we decode again, this time when we decode, when we pull the register file, we can finally get the right value so that the cycle after, we can start executing instruction 3. And later on, you can make progress on instruction 4 and 5 because you free up the hardware. Now, the cycle later, I can keep working on instruction 3 by write back its result. And for instruction 4, because it depend on anything from instruction 3, so we can directly push it to EX, right? And the later instruction can continue decode and fetch. And then once we write back the result, the instruction 5 will be allowed to continue execution. However, if you look at this approach, it would actually add 4 more cycles, and in fact, 5 more cycles if you count the control hazard that was actually 6 more cycles if you count the control hazard that we potentially would have, right? So this is definitely not the solution that we want because we just don't want to wait. So how are we going to deal with each hazard? So let's start with structural hazard. So structural hazard, as we mentioned, it comes with the fact that the hardware doesn't allow 2 instructions to execute concurrently. So if you really want to solve the structural hazard, there's nothing better than modifying your hardware. So for example, if I want to solve the laundry problem, the only thing I can do is to add more washer or dryer, right? So same thing here is that we have the potential structural hazard if we want to allow instruction decode and write back to be done in at the same cycle. So here's the hardware approach that we take, is that it's kind of like tricky because registers,
they are essentially one of the fastest transistors in hardware. So what we do is that for each cycle, we perform the right operation, like the update to a register file, at the first half of the cycle, or you can say it's the rising edge of the cycle. And for the fallen edge of the cycle, we output the register content. So you can think the way how we solve it is that we make the register file only receive inputs and update data in the first half of the cycle. And when we change the cycle edge, we perform the output. So that's the hardware solution. So with that, you can see for the second instruction, for the third instruction, it can, after the first part, after the first instruction, writing back the result at the first half of the cycle, it can read the right value of EAX from the previous instruction. Yeah, but I think this figure is still wrong. But anyway, yeah, so that's the first update we have. And starting from now, you can assume our register file is always in this design. The second thing that we talk about having conflict between two stages is actually both instruction and data, they come from memory. And that's one thing that is so easy to forget. So the solution is actually simple, and you already see it. Why don't we just make L1 cache separate, right? So that's why every time when you pull up your cache configuration from your processor, you will see iCache and Dcache in the L1 level. And we don't do this separation in the L2 because L1, as we mentioned, processor only interact with L1. And we split the L1 and L1 into instruction and data. A main reason is because in this way, we can avoid the structural hazard when to address the situation that we might have concurrent access of instruction and data. And there are also other benefits that people identify having split cache would bring in. So for example, if you think about the locality of your code, it's so perfect in a way that when you have a loop, it has very good temporal locality. And the spatial locality is also so good in a way that whenever you don't meet a branch, it always demonstrates spatial locality. So, and also the code size is a lot smaller, right? So you can imagine separating the instruction cache and the data cache would allow us to better make sure that your code hit rate will be higher because you only need a smaller amount of cache, but it will guarantee that your code is always there, right? But for data, we see higher chances it will be kicked out, it will miss because your data is typically a lot larger than your instructions. And because you need instruction access for every instruction, you don't want your data to kick out important instructions. So it's more preferred to have a separate instruction and data cache design. And a lot of people would code this kind of design a different architecture called hover architecture, because the hover architecture is basically the idea of separating the instruction storage and the data storage. However, to this perspective, you can consider hover architecture is just a division of von Neumann architecture in a way that we have split L1 in the data and instruction, but everything else is still the same, right? So now you understand why every time when I see my processor, I have a split instruction cache and data cache. And I didn't tell you the reason before the midterm because not yet. It's not ready yet to talk about that. But right now, if I tell you, it's because we want to address the structural hazard, then it makes sense. So you can now see the updated figure, right? We have a split L1 in instruction and data, and the data come from the data cache, and instruction come from the instruction cache. Next thing, both 2 and 3 wants to write back. So how are we? The memory unit. Oh, shoot, what was this? What was this slide? What am I trying to say? Oh, okay. So the situation we were talking about is that previously, right, if we don't do anything, then the 2 and 3, they both want to write back at this moment, right? And we only have one set of one set of circuit to write back. However, with this, unfortunately, we still have to store, right? So in this case, that's the only case that structural hazard cannot be resolved through hardware design. Although you can definitely have like 2 sets of write back circuits to solve that. But if I just want to have if I just don't want to duplicate my data paths, the only choice that I can make at this point is to store, right? So this is how we solve structural hazard, right? So first of all, the big thing is that we have a write first, read later register file. And then we have a split L1 cache to address that. So now, let's talk about the second type of hazard. And you can also assume all the processor right now should at least address the structural hazard in providing a register that allows to update in the first half and read at the second half. And also, it has a split L1 design. So let's talk about control hazard. So control hazard, I would say, is probably the second most important issue after we solve the memory problem. So control hazard comes from the fact that we have branch instruction. And branch instruction is essential for most of the programming language to successfully express your logic. So whenever you have a loop, whenever you have an if-else, you need a branch instruction. So for example, here, in this for loop, I'm basically saying that if I is smaller than size, then I can continue. So this is something like, so this is a loop control. And it maps to this, so it's actually implemented by a branch instruction, and a comparison instruction provides its input. So here is compare the R12 and RBX. And if the result is not equal, then we would jump to L5. And for the L5, so one thing that sometimes you might want to know, you might wonder, how can I easily identify a loop? So typically here, I would say typically, most of the time, the loop would have a structure that goes backwards. That's how you can easily identify a loop, right? So you can imagine this is a loop body, right? So so this is the instruction between the loop body, and I think you have already seen enough of this in your midterm as well, right? So another place that we might need branch in this pieces of code is probably this if, right? So for this if instruction, right, you will see we also need to do a comparison, and the comparison is actually happening here. So if it's large, then I would, if it's, okay, so this is less. So if it's less, then I would go to this line of code to code when true, right? And if not, then I will go false through to the next instruction, which is code false, right? So this is another place that you would need a branch. And in the terminology of branch, whenever I am changing the direction from going to the next instruction to an instruction that is not to your next instruction, it's called branch taken. So in this example, we just have the coincidence that when both evaluations are true, we would change our program counter. However, one misconception that I want to clarify, and hopefully I won't see anyone ask this on Piazza. So whenever we have to change the direction of execution, no matter it's going backward or going forward to somewhere that is not your next instruction, this is called branch taken. And there's nothing to do with the true or false in a semantic meaning in your programming language. It simply sees at this instruction if it changes the direction or not. So sometimes a branch, the interpretation of your compiler can make a branch taken when it's false. And sometimes the interpretation would be when the branch is taken, it means true. So it really depends on how you compile your code. So here's the thing, and because this is not a class about assembly language, so most of the time, except for your assignments, I would try to give you some comments and tell you if this is true, it's taken, or if this is false, it's taken. But you should keep it in mind, by branch taken or not, it means I am changing the direction of execution or not, rather than if the statement is true or false. Okay, so why do we care about branch? And why am I saying branch is the next serious problem after the memory? So here's the thing, right? If you look at this sequence from the code that I have given, the branch result is coming from the comparison result. So what does that mean is that before the comparison result is done, the branch cannot make any decision. So there is a data dependency, and it's an immediate data dependency between 2 and 3 here. And as we mentioned, even though we have the optimized register file that allows you to update the result in the first half of your cycle and read out the result in the second half of the cycle, you still can only start executing a cycle later. Otherwise, you won't read the updated register file. So as you can tell, right, for this jump not equal instruction, it has to wait almost as long as the latency of the previous instruction to decide when are we allowed to fetch the next instruction. And before that, there's nothing we can fetch. There's nothing we can fetch because we don't know who is the next yet. So that's why I'm saying this is a serious problem after the memory. So we will talk about how can we address the control hazard in the next lecture. But before you leave the classroom, don't forget, we still have assignment 3 due this Saturday and reading quiz due this Monday. And this is summer session, so we cannot be as relaxed as the regular quarter, and we have deadline coming up and up again. And so one thing that I feel that summer students will probably learn better than the regular quarter is that your skill of time management. And in fact, I think that's probably the most important life skill that would support your successfulness in your career. So doesn't hurt to use this chance to practice your skills in planning your time. And also, we do have office hours are there to help. So don't wait until the very last day, because like last Saturday, I saw a lot of people trying to post on Piazza or send email last minute. And to be honest, we cannot do anything at that time, right? So if you can start early, it will help you and help others. All right, other than that, enjoy the rest of the day. I will see you tomorrow.